Now in the payoff portion of glycolysis, all of the reactions are going to be doubled because we are starting off with 2 molecules of glyceraldehyde 3-phosphate. And what we're going to find is that there's going to be a production of 4 ATP. We use 2 in the first half of glycolysis, therefore our net yield is going to be 2 ATP. Oxidation is going to produce NADH, so we'll get 2 of these. And key elements are the high energy phosphates that we're going to see, specifically 1,3-bisphosphoglycerate and phosphoenol pyruvate. So our first step here is the oxidation of glyceraldehyde 3-phosphate. And the aldehyde is going to be oxidized to the corresponding carboxylic acid. And then we're going to add a phosphate to it, and that's the mixed anhydride that we see here in 1,3-bisphosphoglycerate. NAD plus is going to get reduced to NADH. The delta G under standard conditions is slightly endergonic. However, within the cell, we very rapidly use the 1,3-bisphosphoglycerate, so the delta G is going to be slightly negative in this case. If we look at the mechanism of this reaction, we have a cysteine present in the active site that plays a very critical role. It's when our aldehyde enters, it is going to be attacked by the thiol group of that cysteine. A thiohemiacetal is very similar to the acetal that we see forming between alcohols and carbonyl groups. Once we have our thiohemiacetal, we're actually going to do our oxidation reaction. And the oxidation is done by removal of a hydride. So H with 2 electrons, therefore having a minus charge. This is what's called a hydride oxidation. And that hydride is going to be transferred to NAD plus to make NADH. Once we've removed that hydrogen along with those 2 electrons, the electrons from this oxygen make a carbon-oxygen double bond here, and this is a thioester. We talked about thioesters in chapter 13 being high-energy intermediates. So now we have 2 choices of what we could do. We could simply hydrolyze this molecule off the enzyme, and that would give us a carboxylic acid. But instead of doing that, we're going to bring in phosphate, and that negative charge is going to attack the carbonyl, displacing the sulfur of our cysteine residue, and as a result forming a bond between our phosphate and that carboxylic acid, the carboxylate. So now we have a high energy intermediate in the form of 1,3-bisphosphoglycerate, and we get our enzyme back in its catalytically active state. Now this reaction here is referred to as a phosphorylasis reaction. It's kind of like a hydrolysis reaction, but instead of using water, we're using a phosphate. So we're breaking a thioester bond by adding phosphate across it. The presence of arsenate. Arsenate is an analog of phosphate. Arsenic is just below phosphorus on the periodic table. It can bind to oxygen in a similar fashion to form the arsenate ion, which is very similar to the phosphate ion. However, if arsenate gets used as the phosphate in this reaction, we end up with this molecule 1-arseno-3-phosphoglycerate. 1,3-bisphosphoglycerate is relatively stable to hydrolysis by water. However, water will very easily attack here, displacing the arsenate. And as a result, we end up just getting 3-phosphoglycerate, which is the product of the next reaction. Now, ultimately what happens is that if this gets into a red blood cells use glycolysis as their sole source of ATP. So if high energy phosphates are destroyed, then this can be a very big problem for a red blood cell. In fact, it can lead to the breakdown of the cell and basically hemolytic anemia, which is a pretty dangerous condition. So anyways, this is the basis for how one form of arsenic can be used as a poison. Phosphoglycerate kinase catalyzes the movement of this phosphate group from 1,3-bisphosphoglycerate onto our molecule of ADP to give ATP. Basically, we've got a high energy phosphate transferring a phosphate to ADP, and it's pretty straightforward in terms of this reaction. What's actually going on here is the negative charge on our ADP is attacking the phosphate, and electrons are moving in that direction. Delta G under standard conditions is fairly exergonic. Within the cell, however, it's pretty close to zero. So fairly important to actually have this step fairly close to zero, particularly in the liver, because in gluconeogenesis, we have to do the reverse of this reaction. Once we get 3-phosphoglycerate, we need to move this phosphate from carbon 3 to carbon 2. And the way this is done is through what's called a phosphohistidine intermediate, meaning that there's a histidine present in the active site. We're going to transfer this phosphate to that histidine, and then that phosphate will then be transferred to carbon 2. As we can expect, the delta G in the cell for this is pretty close to zero. The presence of the phosphate on carbon 2 is a little bit less favorable than on carbon 3 because of the adjacent negative charge on the carboxyl group. So that's why the standard state delta G is a little bit inorganic. 2-phosphoglycerate is a little bit less stable than 3-phosphoglycerate would be. If we look at the mechanism of this, here's our 2 histidine residues that are present in the active site. And what's going to happen is we're going to basically start off with one of them in a phosphorylated state. We're then going to transfer a phosphate onto carbon 2, and thus we end up with 2,3-bisphosphoglycerate. Now in a red blood cell, that 2,3-bisphosphoglycerate is actually relatively important because that's actually what we use to help hemoglobin unload oxygen. So a small amount of 2,3-bisphosphoglycerate is made in the red blood cells by this reaction. If we simply want to continue on with glycolysis, we then basically transfer the phosphate off of carbon 3 onto our histidine residue, and that gives us back our phosphorylated enzyme, which is now ready for another round of this reaction. So enolase is the enzyme that catalyzes our dehydration reaction. And we're going to take hydroxyl off of carbon 3, proton off of carbon 2. This is a classic dehydration reaction. So ideally, the enzyme would supply an acid, which would then protonate that that hydroxyl group. That would then leave as a molecule of water, and we would end up with those electrons going in to form a carbon-carbon double bond, and then this proton would leave as the hydrogen. So kind of a classic acid catalysis in this case. Delta G on this, very close to zero, and the resulting product, phosphoenolpyruvate, is a very high energy intermediate, as we will see in the next step. So with pyruvate kinase, what we're going to see is the transfer of our phosphate from phosphoenolpyruvate onto ADP, and we'll see kind of a similar reaction that we saw with the formation of ATP earlier. So negative charge on the phosphate is going to attack. That leaves us with a negative charge on that oxygen there, and pick up a proton, and it gets converted into the enol form that we, that we see here. So that would be the enol of pyruvate. Now, The phosphate transfer, the delta G for that is about negative 23 kilojoules per mole. So that step in itself is highly exergonic. Even making ATP, we see that this is a pretty exergonic step. Now, if we go in and look at this in a little bit more detail, we see delta G for that transfer somewhere around negative 23 kilojoules per mole. The delta G for the tautomerization, however, from the enol form to the keto form is so highly exergonic, that is what drives this reaction to completion. So the delta G for this is somewhere in the negative 35 to negative 40 kilojoule per mole range. So ultimately that enol to keto tautomerism is the true driving force of this reaction.